Welcome everyone to my little talk, seminar, whatever you'd like to call it, on jet engines. For those of you who do not know who I am, my name is Jordan Handy. I'm a student at Virginia Tech. I'm the propulsion co-lead for a team called MachWorks. We are looking to do high-speed jet-powered flight, and my little talk today is to hopefully get everyone familiar and kind of up to speed on everything jet engines, at least everything I know. In terms of qualifications, I'm not qualified at all. I'm an undergrad student. I still have a lot to learn, but I'm probably more knowledgeable than your average person just because this is kind of like my special interest. And yeah, so I'm hoping to kind of bestow that knowledge upon everyone else. So, jet engines are very broad. There's a lot of type of jet engines. Starting off sort of how they work, what fundamentals they use, and kind of what makes them useful to us. So the first thing is they work on the conservation of momentum. So that pretty much says for Newton's third law, every action, there's an equal and opposite reaction. So you push gas one way, the gas pushes you this way, and this is your turbojet. So you're pushing thrust this way, thrust is pushing you this way, and then your plane goes forward, and then you can take off. And it's super, super cool. Jet engines are typically based around like mass flow rate. Mass flow rate is something you can find on the NASA website. NASA has a ton of information, a ton of really good information. They have pictures, they have diagrams, they have paragraphs, equations, all that fun stuff. Mass flow rate is how much air, or how much mass, if you will, you can accelerate in a given amount of time. The more you can do that, the more thrust you produce, because the more you're pushing backwards, the more you go forwards. It's pretty cool. Okay, definition of a turbo machine. All turbojets and other machines are classified as a turbo machine. A turbo machine is a machine that will transfer energy between a rotor and a fluid like a gas or liquid. So this would mean you have your ceiling fan. So this is your ceiling. Your fan blade is spinning this way, and it is using a rotor to impart work on your fluid being air that is being pushed down. So your ceiling fan is a turbo machine, just like your jet engine is. Your jet engine uses some sort of blades, that's an awful picture, but these spin this way around your center shaft, and they do work on the fluid to push it backwards, pushing you forwards. Okay, also I'd like to apologize. A lot of my thoughts are all over the place. I did not organize this well enough, but I'm hoping that within the next hour or so I can kind of get everything out into one place. So, turbojets, conservation of momentum, turbo machines, ceiling fans, all the same thing, kind of. So, when in the early developments of jet engines, most airplanes were using internal combustion engines with your propellers. So you have your little airplane here, and then that is not ideal, but you have your little airplane here, and then you have your propeller that sits on the front. I apologize, I'm not an artist, I'm an engineer. I do the math stuff, not the drawing stuff. And then you have your little engine here. Your engine turns the shaft turns the propeller, whatever, just like your car. Super great for early stuff, not so great if you want to go really, really, really fast. So in the early days, people were looking at this and like, hey, how do we do what internal combustion engines do, but constantly? So internal combustion engines, the 4-stroke ones, have 4 cycles. You have your intake, you have your compression, you have your combustion, and you have your exhaust. So all of this works in harmony. It goes this direction and then loops back to the top again. So in your car's engine, when you rev it, when you turn it on, whatever, your car will intake, so the piston goes downward, sucks in air, then compresses it, so the valves at the top of the engine kind of look like this. You have your cylinder here, you have valve 1, you have valve 2. This one is for the intake, this one is for the exhaust, and then you have your little spray nozzle here that inputs your fuel. So your piston moves up and down in here. This is inside your engine's casing. So intake, this one opens, air goes into here, this closes as the piston is at the bottom, then it compresses it along with fuel, spark plug goes off, blows up essentially, pushes the piston downward, and then the piston goes back upward, because that was your combustion cycle. And then now you need to get all that excess gas out of there, so then your piston pushes back up out of this one, and then it starts all over. And that's how your engine works. So, all engines work on this cycle: intake, compression, combustion, exhaust. Jet engines, instead of doing this 1, 2, 3, 4, 1, 2, 3, 4, do it continuously, all at the same time. And they do that in a few different ways. There's a bunch of different classifications of jet engines. So, let me write those out. Damn, this is not erasing like I wanted to, but that's okay. Put that there. So, okay. So we have your pulse jet. We have your turboprop. We have your turbojet. We have your turbofan. We have your ramjet. Whatever. And then we have your scramjet. Damn. Okay, so pulse jets are technically the simplest. They were used in World War I by the Germans to make their V-1 flying bombs. They're very scary, they're very loud, they're, like I said, very simple. Technically speaking, it's a straight tube. You can get away with putting a tube in a line, put a spark plug, put a fuel line in it, and bam, you got a jet engine. Oversimplifying, but for the case of this, it works. So there's two types of pulse jet engines. There is a valved and there is a valve-less. So as you can kind of understand, one of them has valves, one of them doesn't. The valved engines look like a straight line and work like your car's engine, where you have your intake and your exhaust cams. You have your combustion happening here, and everything goes out the end that way. So just like your engine goes up and down, which is a reciprocating internal combustion engine, this one does the same thing, but does it in one direction. So opens to intake air, closes, sprays fuel, combusts out the back because it can't go this way because these are closed. Then once that happens, the cam opens again to get another intake, and it pulses, and then it does that really, really quickly, which ends up giving you thrust. But because you're essentially detonating multiple times a second, you get a whole lot of vibrations. It's pretty inefficient. It's really, really loud. It'll like vibrate you. There's been some development issues with that. Kind of the reason why we don't use these anymore. But yeah, they're really great. They're pretty simple. Valve-less are typically shaped like a U, so they look like this. So air goes in one way, out the other. This is sort of an oversimplification. There's YouTube videos that you can find. People build them all the time. Fun fact, you can also build a valveless engine out of a jam jar. It's pretty simple. You pretty much just drill a hole in the top of your jam jar, put some fuel in it, shake it around, light it, and it will do its thing. Really weird, really funny. Sometimes they explode, so be careful if you do that. But same kind of idea where the air comes in, mixes with fuel somewhere around here, combusts, goes out that way. That combustion causes a pressure wave to go outwards. That pressure wave now is low pressure once that exhaust is expanded. So then it draws air back in where it can combust again. And then that happens and happens and happens and happens. And then you get thrust. It's pretty cool. So, turboprop. Turboprop are still in use today, mostly by smaller jets. A turboprop takes the idea of a internal combustion engine and puts a jet on it, hence the turbo. Turboprops are used on smaller aircraft, like I said, with turbos, propellers. And let me draw this here. Turboprops are a jet engine that is strapped to a propeller. So this comes in two forms on airplanes. Excuse me. The prop goes at the front. On helicopters, that prop goes at the top. That is called the turboprop is for the plane. The turbo shaft is for the helicopter. So you have your jet engine here, air goes in the front, exhaust goes out the back. For a propeller, there's a turbine here, which I'll get into the specifics of turbojet engines, these two. But essentially this spins because the exhaust gas is going through it. And so you have a shaft that's attached to the center of your engine and the back. So as your exhaust goes here, this spins this way, which also spins this shaft. And this shaft is attached to your propeller in the front. And your propeller pushes air backwards, which based on Newton's third law that we covered, pushes you forwards. So that's for an airplane. For a helicopter, it's the same thing, except instead of the shaft going forward, it goes upwards out the top. And then you have this, so this spins this way. It does it through a gearbox. These gearboxes are very fancy, they're very expensive, and very hard to make, but it works. And then you have a helicopter that pushes you upwards instead of forwards, which is really useful. Turbojets. Turbojets are the earliest type of jet engine. When people were looking at the internal combustion engine, like I said, they were like, hey, how do we do this at the exact same time so you just get constant power output instead of push, 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 like what a pull shit does. The early turbojets function like a turbocharger that you would find in a car. And there's two types of, well, I guess technically these are both turbojet engines, turbo machines, whatever. There's axial and there's centrifugal. So turbojets are centrifugal and they work like a turbocharger in a car. So you have your turbine here and you have your housing, not like that, your housing here, like that. So this is all a blade. So your air comes in here and you spin this a couple different ways. Let me give ourselves some more room. So you spin this shaft. Most turbojets function on the idea that everything's kind of attached to the main shaft. The exhaust spins the shaft, which spins the intake, which then pushes it back. So you spin the shaft, and this rotor, which is shaped somewhat like this, will spin really, really fast, and as it does, it draws air in and then flings it to the outside. So as this thing spins, the air's coming in and getting shoved to the outside as more air is coming in behind it. But as it's doing that, this area in between here is getting smaller. So as you're flinging it to the outside and shoving it through your engine, you're compressing it like what you do in an internal combustion engine. As your piston goes up, it compresses the air. This one just does it by flinging air to the outside, but reducing the volume that it can occupy. So once the air is compressed, it then goes around your turbine into your combustion chamber. Combustion chambers are a topic in their own. There's a lot of different ways that you can design them, depending on what you're looking to get out of them. But in essence, it's a way of ensuring that your air can combust even under these kind of harsh environments where you have high pressure air that's moving really quickly. So you combust the air inside your combustion chamber, and then it goes out the back, which then spins this central shaft. And that central shaft turns your rotor turns draws your air in, flings to the outside, compress, and this whole cycle continues. Turbojets are great, especially when compared to your internal combustion engine. They have a higher power to weight ratio. So for the same amount of weight, your turbojet is going to produce significantly more power than your internal combustion engine. However, they only work up to a certain speed. Generally speaking, turbojets work, let me get the red, from 150 to about 400 miles an hour. So they're great, especially in like early World War I, World War II, that kind of stuff. Don't quote me on that, I'm not a history major. World War II, maybe not World War I, but they're super great. They're better than internal combustion engines. They're more efficient, they're faster, they're lighter, all the great stuff, but they only work for relatively low speeds. And if you're like me, you have an itch for speed, you want to go fast, 400 miles is, at least airplane-wise, not that fast at all. So, how do we get around this? Well, we need our engine, our turbojet, to be more efficient, and we need it to go faster. That's where the turbofan comes in. Let's draw a line here. So your turbofan, instead of having a rotor that compresses everything, it has rotors and stators. So your turbo fan sort of looks like, actually, let me get some more room. We're gonna draw right down here. And then we'll do this. Give ourselves some more room. Okay. So your turbo fan is exactly like it sounds. It's a turbojet that has a fan instead of a rotor. So your turbojet has an interior part that sits like this. This is essentially everything that's going on in here. So your combustion chamber, this is where it compresses everything, but it also has an outside casing that sort of tapers like this. This is your nozzle. And so you have this big old fan that sits right in the front, like this. Like I said, I am not an artist, but your fan will sit like right up against your housing. And so this shaft is contained all the way through. And so what it does is you have your bypass air. Bypass air is just air that bypasses your combustion chamber. It just goes straight through your engine. It's great for cooling, great for efficiency, all that fun stuff. So it does that, but also it forces air into here. This air then meets your combustion chamber where you add like fuel and whatnot, combust, goes out the back. So this air continues through here and meets here. So then you have high temperature, high pressure air here, and you have low temperature, high pressure air here. And all that comes together to make a really efficient, really great engine. Everyone loves these, especially the airliners, because they're super efficient. You can get pretty good speeds on them. I believe that most of the commercial airliners cruise around 500 miles an hour. I could be wrong on that. I'm not super well versed in the commercial stuff. Like I said, I am an undergrad, so there is still a lot I need to learn, but definitely higher than this, more efficient than this. So everyone loves these. These are what the military uses. These are what commercial airliners use. Pretty much every engine, every modern engine is a turbofan. The only problem with turbofans is they are very, very hard to make. There's a lot more parts than in a turbojet. There's a lot more parts that are under stress, which is where like the material science comes in. There's titanium, there's steel, there's alloys, all that fun stuff that helps you get the most out of this engine, which we will get into. But now that we have this, we're gonna move on to ramjets. And all of this is pretty much building up not only over time, but over speed. So now we're able to go faster and faster and faster and faster. And that's where your ramjet comes in. And so your ramjet, I forget exactly what the acronym stands for, but it functions on the property that you're already moving fast. So with your turboprop, your turbojet, your turbofan, you as the engine, if you will, need to compress the air before you can combust it. And I guess I should have covered this earlier. So air is a gas, right? So there's a bunch of little molecules over here that occupy this volume. If you want to get more energy out of this air, you need to compress it. So you need to turn this big volume into this little volume that has way more air molecules in it. And when you do that, you can then add fuel, and that equals combustion. Everyone loves combustion because that's how you make things move. So you compress, going from here to here takes a lot of work. And each of these engines does it in a slightly different way. Most work on the same property where you're kind of shoving air through your engine. You're just keeping it moving, but you're decreasing the volume that it can occupy, so you're pushing the pressure up. And when you do that, you can get more energy out of it. So your ramjet, instead of like your turbojet, turbofan, whatever, where you need to spin something to move, your ramjet says, hey, we're already moving really quickly. What if we just use the fact that we're moving quickly to compress the air? So your ramjet is essentially a straight line that kind of tapers down. So as you're moving quickly, your air is occupying a smaller and smaller and smaller volume. So it's forcing the air to compress itself, essentially. This is actually sort of misleading. Let me draw this a little bit better. So your ramjets, they have their outer casing that looks like this, and then they have typically a nose cone that sits like here, like this, and this is kind of what tapers to the outside, like that. Here, and so as the air is coming in here and here, it's getting compressed as it gets smaller and smaller and smaller and smaller and smaller. And then once it hits here, this, just behind where this nose cone sits, you'll have a flame holder. And a flame holder is exactly what it sounds like. It holds a flame to ensure that as you're pushing all this air through, you can still combust. Because combustion still requires some sort of start, some sort of chemical reaction, some sort of spark or flame or something to get it going. So, just behind your intake nozzle, you have your spark plug, you have your fuel line, all that fun stuff. And so that combusts here, which then combustion happens this way, goes out that way, and so you're still moving forward. The only problem with a ramjet is because you're moving so quickly, if any of you have ever tried to use a barbecue lighter on a very windy day, you can understand how hard it is to light something on fire in really, really high winds. So, to combat this, because if you're moving supersonic, what a ramjet does is it uses the geometry of this nose cone, either by moving it forward, changing its diameter, whatever it may be. There's a lot of different technologies that go into this. They slow the supersonic air that's coming in the front here to subsonic air so you can combust it, and then that combustion pushes it out supersonic again. So you're fast air in, slow it down to combust, and then push it out really fast again, and that pushes you really, really fast. So then, someone had a grand idea, and they're like, hey, what if we take a ramjet, and then instead of slowing it down to subsonic, we just keep it supersonic and just go even faster. And there's supersonic, so scramjets or supersonic ramjets are the same thing, but instead of slowing down to subsonic to combust, it just goes straight through. Combustion happens all at once as the air is still supersonic. So it still compresses it like that, it still combusts it, it just does it at faster speeds. And scramjets are where there's a lot of technology still developing. There's a lot of opportunity for new players to come in instead of your Boeing, your GEs, all these companies that have been doing this kind of stuff for years. There's a lot of technology going on there. And that's because as we get faster and faster, not only can you as a commuter get from New York to Los Angeles to London, wherever you need to go around the world quicker, but we can develop fighter planes or bombers or transportation, whatever we need to get places faster. Time is of the essence. So now that we have sort of outlined all of our engines, we're gonna make a nice little line that sort of covers where each of these engines operates within. Okay. So, we have our nice big speed line. Starting from here, which is 0. These are all your Mach numbers. Your Mach number is your ratio of your current speed to the speed of sound. Your speed of sound changes based on your altitude, so it's kind of relative, but it gives you a great idea of how fast am I going? Mach 1 is pretty fast, Mach 2 is really fast, and then as you climb up, obviously everything gets faster. But if you're like, hey, I'm going Mach 0.1 at sea level, you're like, okay, you're really not going that fast. But if you say hey, I'm going Mach 3 at 10,000 feet, you're like, okay, you're really screaming through the air. So we have 1, 2, 3, 4, and then 5 plus. It keeps going and going and going and going and going. So, is your current speed to the speed of sound. I believe that's correct. It could be the other way around, but it is your current speed to the speed of sound. So it's a ratio, like I said, that just kind of gives you a better idea because your speed of sound changes with how high up you go due to the changing air density. So your turbojet. So that's the one that uses the spinning impeller that spins around and flings air to the outside to compress it. Let me write these in some different colors. I'm gonna get fancy with it. So your turbojet, these were turbojets for the early ones, will go, generally speaking, to about Mach 3. And there are some limitations, there are some special cases, like if everything's ideal, it could go faster, it probably usually goes slower. Like I said, these aren't really used today, so they don't really matter as much. But yeah, let's go back to, and let me write this in miles per hour. So Mach 3 is about 2,300 miles per hour. So you're moving pretty good, especially for an airplane. Mach 3 is pretty fast. Most of your fighter aircraft will generally go about Mach 2, and that's with engine augmentation, which is something we will get into. Your turbofans can push pretty much about the same. Generally speaking, turbojets, turbofans work about the same. Turbojets just do it more efficiently. So those will also go to about here. And like I said, there are a lot of cases that, like, maybe it doesn't go that fast, maybe it goes even faster, whatever. So general case, take it with a grain of salt. Your ramjet is where things really start to get fun. So you have your ramjet, and that starts, I should probably move that over. And so like I said, ramjets function on the idea that you're already moving quickly. And so they're not gonna, generally speaking, they're not gonna work at your low speeds. Technically, they could, but they're really inefficient. They're really not gonna give you much thrust. They're really just suited for kind of high speed stuff. And so your ramjet functions between about Mach 3 and Mach 5. And where is it in my notes? So sometimes they can get up to Mach 6. So let's add another line here to 6. And put a line here, and then we're going to do dotted because there are some special cases. But that Mach 6 upper limit is 4,600 miles per hour. So you're moving really fast. Even at Mach 3, going from pretty much coast to coast on the US, Mach 3 will get you there in about an hour. So that kind of puts it in perspective. You're really moving fast. There are other reasons why you're not allowed to do that, which we will get into in the later parts of this talk. Ramjets are used for, generally speaking, missiles, things that don't have people on it, just because you're moving so fast. And when you have a person on board, you need to include a lot of extra stuff that takes up space away from your fuel, space away from things that could be used just to either, generally speaking, blow something up or push it faster. So yeah, and then your ramjet is when things get real fun. So your ramjet is a supersonic version of this, like I said. So these only function at like really high speeds. And so your ramjet, generally speaking, your scramjet, sorry, supersonic ramjet. Rewrite that. Your scramjet will go way out here to Mach 25. And when you hit that point, you are screaming, man. Generally speaking, these are your missiles. Your missiles, your stuff that goes into orbit and then re-entry, and you're moving real fast. These are your spacecraft that are coming back from orbit or coming back from the moon or whatever it may be, and they're entering the Earth, and they use the Earth's gravity to just scream back into the atmosphere. Yeah, so now that we kind of have an idea of where everything lays speed-wise, we can start classifying some of these different regimes. So you have your Actually, let me just do it here. Let me draw a new line. It'll be easier. So there's 4 different types of sonic regimes, if you will. So we have Mach 0, which is you're not moving at all, up to about Mach 3, and just a word is a lot of these are about, because they're generally speaking is no like one specific number that's like, okay, below this you're in one regime, above this you're in another. It is just kind of like, okay, about Mach 0.3, about Mach 0.7, whatever it is. So 0 to 3, you are subsonic. So subsonic means your air is treated as an incompressible gas. So if you've ever tried to put air in a syringe and push it closed, you can realize that it's like really, really hard to do that. Incompressible gases and liquids are things that like are used in pneumatics or hydraulics to move really, really heavy loads because they're incompressible. So subsonic, 0.3, everything's really nice. Everything plays really great. You're not going too fast, you're not going too slow. Everyone's having a good time. So then you go from 0.3 to 0.7-ish. I'll put a tilde in front of these so you can know that it's like, okay, about there. And this is where you get into transonic. And so your transonic is when things start to get really unfun calculation-wise. You're not quite supersonic where your air becomes compressible. You're not quite subsonic where air is completely incompressible. You're kind of in the middle, especially as you get up towards 0.7, where things get a little screwy with like, okay, some of your air is incompressible, some of your air is not. It's kind of in between, kind of feeling things out, figuring out what it wants to do, which just means that it's a nightmare to do calculations. But this is where a lot of aircraft live within. Your commercial airliners live somewhere in here. So there is a lot of knowledge. It's just really unfun to do. And then, as you get up to Mach 1, Mach 1 is where you are perfectly sonic. And I should actually say that like transonic goes to like way up there-ish. I believe. Let me double check my notes. I apologize. I should be more prepared for this, but I'm not. Either way, so Mach 1 is, you're perfectly sonic. So Mach 1 needs your speed matches the speed of sound, the local speed of sound, because it changes based on altitude perfectly. So this and this are the same number, which means your Mach number is 1, which means you're going exactly at the speed of sound. And I guess I can cover it in a little bit. As you approach Mach 1, it gets really, really, really hard to go faster. So here, as you're building up, it gets harder and harder and harder and harder, and it just kind of exponentially increases with the amount of power you need to get to Mach 1. And then once you get past Mach 1, the things kind of level out and it gets not so hard. Not so hard is relative though. So subsonic, transonic, sonic, and then you have supersonic, which as it may sound, is above Mach 1. And your supersonic goes to about Mach 5, I believe. So your supersonic is Mach 1 to Mach 5, so that would be from here to here. So that would include your turbojets, your turbofans, at least on the sort of higher end, your ramjets, not necessarily your scramjet yet, because you need to go fast for this. And so you have your subsonic where things are nice, transonic where things are changing, sonic and supersonic are where your air becomes compressible. So now you're moving so quickly the air can be compressed, so then everything changes. Your equations change, your numbers change, but you're going really, really fast, which is awesome. And then you get out to this little bit right over here, and this is hypersonic. Hypersonic is where a lot of research happens. That's poorly written. Hypersonic. Hypersonic is above Mach 5. Hypersonic extends, at least to my knowledge, up into you can't go any faster anymore, which Mach 25, Mach 30, I don't know. Like I said, I'm an undergrad. This is just like stuff that I find interesting. But once you get into your hypersonic regime, everything changes. So as you get up closer to sonic, your air starts changing, whether it's compressible or non-compressible, and that changes everything. Once you get into your hypersonic regime, that's when things get really, really like unfun, because now you have chemical reactions happening. Because you're moving so quickly, the friction between your aircraft and the air itself slamming into one another causes chemical reactions, it causes a lot of heat, and that's really, really hard to deal with, which is kind of like what NASA does for their spacecraft as they're coming back in. They're hitting the hypersonic numbers where you're Mach 25 or Mach 20 or whatever, and you're going so fast that the air around your aircraft starts heating up. Chemical reactions take place between the air and your aircraft's material, and so you need to kind of manage that, manage the heat, make sure your aircraft doesn't disintegrate as you're coming back into orbit. Okay, that covers that. Now, probably should have done this earlier, but we're gonna start getting into turbo fans and how they work, their different parts, and all that stuff. Just kind of wanted to give an overview before we move on from the turbojets and your pulse jets and all that stuff. Your pulse jets work on like the lower end, if I didn't cover that. So, you have your turbo fan. And so let's draw a little picture. Let's see if I can draw a little picture. So you have your engine housing, and you have your center axis, whatever it's called. And so you have your fan here. So you have that, and then you have your big old fan blades, and these actually go to here. They perfectly match up with the edge, and so this kind of creates like a ducted fan, which is really great for efficiency. Not something I'm going to cover because it's not something I'm super knowledgeable about, but you have your turbo fan like this, and then you have your interior part of your turbo fan. So, like I said earlier, turbo fans have bypass, and so this area will change, your fan area will change, so this can become bigger, this can become smaller, based on whether you want a high bypass or low bypass. Generally speaking, the airliners use high bypass because they're more efficient. The military, like your fighter jets, your bombers, whatever, will use a lower bypass, so this area will be just a bit smaller than what's found in commercial. So your air's coming through here, just like that. All that fun stuff. So, we need to compress the air before we can combust it in our combustion chamber. And we do this through spinning blades. And so to do that, we're gonna do a couple things. We're gonna divide this up into a hot side and a cold side. And this should actually, yes, cold side. Hot side, cold side, high pressure, low pressure, differences. Okay. Excuse me. So, your cold side is exactly how it sounds. It's your cold side of the engine. There's no heat. That's your front side of the engine because your air is flowing through. You haven't combusted anything, so nothing's getting hot. Everything's great. The only problem with your cold side is you have really, really, really high pressures. And it does this through a series of stages. And they work like this. Your stages will get smaller and smaller as you get closer and closer. So hopefully that kind of tapers inward like that. And so these are all your blades. So you have your stator and your rotor. Your stator stays still, your rotor spins. Hopefully I use those words correctly, but point still stands. These bits spin, the parts that are attached to the engine housing don't. So all these blades, these fan blades, they're all like this. They're all very thin. They're all very hard to make. You got to make them out of like titanium, which is really expensive, really hard, but like a really, really great material. It's kind of the reason why only a couple of companies make engines like GE, Rolls-Royce, Pratt & Whitney, is because it's hard to do that. So these blades spin with your turbo fan blade, which spins with your central axis. So this is called a axial turbojet because everything runs along an axis. your turbojet that spins and flings everything outward is called the centrifugal turbojet because it flings everything outwards. It centrifugally compresses stuff by spinning. Centrifugally just throws everything outside. So let me finish this. So you have all your fan blades, right? Like this. And so your engine housing will kind of taper in along like this. So what you're doing here is you are compressing the air. So you're closing that volume, so you're shrinking the area that the air can occupy, but you still have the same amount of air that needs to occupy that space. And so to do that, you're compressing the molecules together so you can get more out of the combustion process. So to do that, you can't just have the blade spinning like this. You need stators. And stators are another set of blades that are attached to the engine housing and don't spin. So I'm going to color these in to hopefully distinguish between the two, like this. That's kind of messy, but the whole point is your stators stay still, and these are on your engine housing. Your rotors spin with your axis, so your central axis of your engine, and they interlock between each other. And the tolerances between those are very, very small. Because you don't want because if you have large spaces, then you give the air an opportunity to expand into that space. You don't want that. You want it to compress into here before you combust it. Then it can expand, then you can get more thrust. So, and this is on both sides between here and here and here and here. And the cold side of the engine is hundreds of blades. And they range from 4 or 5 inches or 6 inches or whatever. I haven't actually been able to measure them. Generally, companies are pretty keep a watchful eye over that stuff, but the blades will slowly incrementally shrink to where you're going from this big of a blade down to like this big of a blade, and so they're tapered, they're like twisted and all this stuff, which you will hopefully, if you're interested, learn about in one of your later classes. There's a lot of math behind it, there's a lot of calculations, stuff like that. So this is your cold side. So now we have our engine spinning and we have our bypass air going through. We have our air, it's going between the rotors and stators that are compressing it and shoving the air really, really close together. And so now we get to here. And this line is where you hit your combustion chamber. So this is kind of the line between your hot side and your cold side. It is right kind of where this blue, green line, whatever it is, right here. So now you have this really, really high pressure air that you've just put a whole lot of work or energy, burning your fuel, into compressing. So now that it's compressed, you have your combustion chambers, and this is where your hot side starts. And so your combustion chambers are these like soda can-ish, they're like tubes. That kind of, so if your engine is a circle like this, that was a pretty good circle. You have your center shaft here, and you have combustion chambers around like this. Sort of like a revolver. So these are evenly spaced, they have like holes in them, so you have, it kind of looks like this if you're looking side on like this, and they have like big holes that get like progressively smaller all the way down, and that goes around the whole thing. Those go in here, and those fit this way. So this is a front view, this is a side view. So you have your, inside your combustion chambers is where you have your fuel getting injected and where you have your flame holders. Like I mentioned earlier, your flame holders just make sure that you can combust the fuel, because you need something that will start combustion, because generally things don't like to blow up on their own, with a very few exceptions. But yeah, you want to also make sure that your flame doesn't go out. So that's why you have your combustion chambers, because the front will protect it from all this air coming in. And so your flames are gonna sit like here and here and here. There's like different designs, you can look it up. But generally it's like this, and then you have your fuel that gets injected like here, or actually rather down the center. And so as it combusts, it goes out these holes, this way, this way, this way, out from all of these. And so that's your combustion chamber. That's this whole section. So your fuel, you now have your high pressure air, you have your fuel, you have your spark or your flame holder. And so bam, you get combustion. But generally combustion wants to expand equally in every direction. And the problem is we have air here. So this air is essentially creating a wall. So that forces everything to go this way. And this is your hot side. So your air is now being forced this direction. It's really high temperature, it's really high, it's high pressure, it's high velocity. Everything's moving really, really quickly towards the back end of the engine. Let me erase this so we have some room. So in an internal combustion engine, to make sure that the engine keeps itself on time, keeps running, you have a flywheel. A flywheel just keeps everything moving by storing momentum. It's really heavy, it's hard to start up. Once it's moving, it's hard to slow down, so it just keeps everything moving nicely. In a jet, the reason that they take so long to spin up is because you have a lot of mass here. You have all these blades, you have all these parts, you have this big old fan blade on the front, and that takes a lot to get moving, which is why they take like a cart or a motor or whatever it is to get things moving. Once they're moving, they're great. And so once they are moving, to keep them moving, you have a turbine. And a turbine is essentially a reverse of your cold side that sits at the back of the engine. So it's like this. There's generally like a couple of them, a couple stages that are all like together. And so what happens is as your air that you've just combusted moves through this, it spins your turbine blades, and your turbine blades are attached to this center axis. So as your turbine blades spin, because the air is moving through them, it causes them to move. It spins this axis. This is then connected to all of your front stuff, which then spins your fan, spins your blades, spins your cold side, gets all that moving. And so it's kind of a self-feeding process. So you have your air, which you put work into, you combust it, so you give it a whole lot of energy, and then you just take some of that energy to spin these blades to keep the whole thing moving together. And that's kind of how everything cohesively works. But you want to go fast. And to go fast, based on the momentum equation, you need to push a whole lot of stuff backwards really quickly. So to do that, you have a nozzle. And on your military jets, on your commercial airliners, on anything that wants to be efficient and run properly, you have a variable geometry nozzle. And all that means is your nozzle that is a circle at the back of your engine can then move to a small circle based on your speed. And so it kind of looks like this, where this here is where all your air is coming from, this is where your air is leaving from, and these points will go out here, like this, like that. So it'll go open and close based on how fast you're going. And the point of a nozzle is to accelerate or trade your high pressure air that's coming from here into high velocity air. So you go from high pressure to high velocity. High pressure, high velocity. And you're doing that because based on the conservation of momentum, the more stuff you push backwards, the more stuff can get pushed forward. So if I push you backwards, you'll equally push me forward. You don't see this on Earth because we're standing on the ground, gravity, friction, whatever, but if you go into space and you push someone, you'll both equally go opposite. Granted, you won't go the same speed or whatever based on your mass and all that fun stuff. But we now trade our high pressure and we shove it down here again, or if we don't need to, we can keep it open. So then it pretty much just flows straight out the back. We also have our bypass air. It's coming through here like this. And so everything meets at the nozzle. And so what your nozzle does is it trades high pressure, high velocity to go here. And so you get a whole lot of high velocity out the back, and your high velocity out the back means you have high velocity pushing you forward, so then the whole thing moves forward. And that's kind of how your airliners move. They push a whole lot of stuff at the back. You constrict the flow so it's going really, really fast, and you get a whole lot of thrust forward. Yeah. There was something that I was going to cover that I forgot. What am I missing? let me see. Yeah, so these have limitations. So as you can imagine, if you want to do this all really fast, if you want to go faster, this needs to spin faster, these need to spin faster, this needs to spin, everything needs to go really, really fast. The only problem is your blade, so you have your center axis here, you have your blades that are all here and kind of like a sunflower, whatever. These all go, let me draw it around. Probably should have taken an art class before this, but okay. So this is your engine. Poorly drawn, but it's your engine. And these are all your fan blades that are here. So if you've ever been to a park and they have those little spinny things and you've sat on the very edge of it, you're moving a lot faster than if you sit in the very middle of it. It's the same principle that is the reason that we need car differentials. So I know this is kind of off topic, but you have your car, so you have a wheel and a wheel that go here. And as you're going around a turn, as you can see from here, this arc, this distance, is a lot shorter than this distance. So your outer wheel needs to move a lot more to be at the same position than your inner wheel. And it's the same concept here, where your blade can be thought of as sort of your set of wheels. And so the inner part of your blade, the part that's attached very, very close to the axle, needs to only move a very small bit. But with these big turbojets that are the size of a person, whose radius is 5 feet, your outside here is quite the distance here. And so to move at the same speed as this, it needs to cover a whole distance in the same time that the inner part covers the small distance. And so your outer part of your blade is moving a lot faster than the inner part of your blade. And so as you're spinning, your force is trying to push that blade towards the outside. It's trying to rip it apart, which is another design point that these companies work around. So, yeah. So as you're doing that, if you want to go faster, this needs to spin faster, everything needs to spin faster, but you also have the outside of your blade that needs to cover the same distance as the inside of your blade. But it's moving so fast that what happens is, as you're going faster and faster and faster around, the outside, the very tip of your blade here, is going to approach supersonic speeds. So the tip of your blade is going to be supersonic, the bottom of your blade is going to be subsonic, and that causes a lot of really bad issues. A lot of bad issues that can cause your engine to get completely blown apart. And so that's why these only function up to a certain speed. However, there's something we can do to remedy that. And we call that engine augmentations, which essentially just means, how can we extract more energy out of this process without increasing speed? And so some of these engineers, who are way smarter than me, came up with this thing called an afterburner. An afterburner is really, really cool. And I guess, sort of as its name suggests, it burns fuel, it burns the air again after the combustion process. So what you have now is your afterburner is almost, can essentially be simplified down to a straight tube. There's another combustion chamber inside it that is the same as these, excuse me, but it doesn't have any of these moving parts. So you also have a nozzle down here where your flow will come out. And so what happens is, as your air is coming through here, when you burn it in here, you have a whole lot of air that's been compressed down. You have fuel. The only problem is you can't combust it perfectly, because if you do perfect combustion, it's going to melt all this. And these parts are very delicate because they're spinning. And so what happens is, when you get your afterburner, you still have some leftover energy in your air. Your air hasn't been perfectly combusted. And so an afterburner will add, probably not here, in here, will add more fuel and use the excess air that's coming from here to combust again, but it can do it more perfectly, if that's a word, to get more energy out of it. So the afterburner runs a whole lot harder than your engine because it doesn't have any of these spinning parts to worry about. And then it does again the same thing with the nozzle, which constricts or expands based on the speed you're going to accelerate your gas as much as you can. So there's another cool thing you can do, which is what the SR71 did, and you have your bypass ducts. Instead of going to your nozzle, they feed into your combustion chamber, like this. And so what you're doing is you're taking fresh air, mixed with your combust air, mixed with more fuel, all combined together to get a whole lot of power. And like I said, you can combust closer to perfection because you don't have to worry about any of these sensitive spinning parts melting or warping or any of that. You just throw a whole ton of stuff out the back. The only problem is the afterburner chews through fuel like no one's business. You'll turn your 2-hour flight time into like 10 to 20 minutes because your afterburner is just dumping fuel into your exhaust stream. But in the exchange of that, it's like your NOS button on a car. You hit it and you're just gone. And so these engines will only, or these aircraft will only use your afterburner when you either need to get somewhere very quickly or you need to escape somewhere, generally speaking, or you're taking off and you need to climb. But otherwise, they're just using your regular turbojet stuff. Yeah. So now we have our jet, we have our afterburner, we have how it all works. There's another part of this system, and that is your intake. So on your commercial aircraft, your Airbus, your Boeing, you have your plane that sits here with its nose gear, it's poorly drawn. You have your wings here, you have your tail here, and your little pilot, whatever. I'm bad at drawing. You have your rear gear. So engine 1, engine 2, maybe 3, 4. You could also have one in the tail, whatever it is. This is what your commercial aircraft do. They mount the engines over the wing because they need the fuselage to carry passengers, to carry cargo, to carry whatever they want to carry. And so these have nacelles. Nacelles are just the housing of the engine that is then attached to the wing. However, with military aircraft, you want to decrease your radar cross-section return. And if you have your engine here, a radar can read this entire point. And that's going to come up as a really big return. So to solve that, military jets will put your engine in the middle. So you have your aircraft here, like this. You have your wing, and then they have their engine that sits in here, in the middle. Could be worse. You have your little person here, and then you have your exhaust that comes out the back. That's why, like on these aircraft, you see that they have like one hole or two in the back for their two engines, like this. You have your tail, whatever, stuff like that. But because your engine's now in the center of your aircraft, you're gonna get the air from outside to inside. And so to do that, you have your intake. And your intake needs to deal with a couple of things. With your intake geometry, you need to make sure that you can accommodate the maximum mass flow rate. So when the engine is at max power, it's sucking all this air in. You need to make sure that your intake can handle that, because if it can't, you'll choke your engine, which means your engine can't get enough air into it. And if your engine can't get enough air into it, it'll either stall or won't produce enough power for you, which is not good. And so there's a couple ways to do this. There's whole fields dedicated to this kind of stuff. For our purpose, we're just gonna cover the very, very basic stuff. So let's say you have a belly mounted intake. So your intake comes up here, and then you have your engine like this. So this whole engine is here. And then you have your afterburner and your nozzle like that. So your intake needs to get the air from the front to the front of your engine, to here. But it needs to do that in a very specific way. So there's intake performance, There's ram drag, there's a whole lot of stuff that needs to contend with this. And so we're gonna start with intake performance. So your intake performance measures your pressure recovery, which means as your flow comes through here, how much pressure is lost between your the front of your intake and the front of your engine. So when you get to the front of your engine, you want as high pressure as you can, because then you're doing less work to compress it here. Because all you're doing here is you're increasing the pressure and decreasing the volume, but if you already have high pressure coming in the front, then you don't have to do as much work, and then you can save on fuel. So that's your intake performance, but as it's coming through here, whatever your geometry may be, the flow, as it goes through, can get all messed up, and that's bad. So for a turbo fan, you want the pressure distribution across the front of your engine to be even. And that essentially means you want the pressure here and here and here and here and all around your circle to be the same. Because if it isn't, if your pressure, let's say here, is smaller than your pressure up top, what happens is as your blade is spinning in a circle, the high pressure is gonna push your blade back just a little bit, and then the low pressure is gonna, as it gets to the bottom, is gonna push it forward just a little bit. And so what happens is as the blade is spinning around your engine really, really fast, the blade is gonna start wobbling back and forth and back and forth. And what that'll cause is, let's say right here is where it starts to wobble about, it's gonna cause fatigue. So if you've ever had a paper clip and you bent it, you're like, okay, it can deform. And then you bend it back and it gets a little bit easier. And then you bend it back, you keep doing that, and then eventually it just breaks. That's what's gonna happen to your turbine blade, because it's getting forced back and forth, back and forth, back and forth, thousands of times a second until it breaks, and then the whole thing blows itself apart, which is very bad. So you need to design your intake so that the pressure across the front of your engine is equal, or at least close to equal, at all these points, which is great. But as you're doing that, you need to contend with something called ram drag. So as you're moving really, really quickly, your intake can only handle, like if you imagine your intake as a cup, theoretically, your intake can only handle this much volume at a time. So if you're moving faster than this, then where's the air supposed to go? Like imagine you have a cup and you put it in water. As you push that cup through water, it's gonna start filling up with water, but then as it gets full and you keep pushing it forward, the water doesn't know what to do and it's gonna end up spilling around. So that's what your intake happens is once this volume gets filled up too quickly, so the intake cannot handle how fast you're going, the air will start coming in here and then getting forced back around. It'll come in and get forced back around because there's already too much air in here. Like you're still moving, air is still moving through here, but the air coming in the front is faster than what the engine can take in. So then your air starts getting shoved around and then you start getting ram drag, which is this here, starts causing drag on the front of your aircraft, means to slow you down, a bunch of really, really unfun stuff. So you want to avoid that by designing around that. However, there's another thing we need to cover. Your intake needs to contend with a different variety of speeds. So your intake design at Mach 0.3 is going to be different than your intake design at Mach 1.3, just based on how fast you're going. To get your even pressure distribution, you need to make sure that your air is coming in at subsonic speeds. This is for just about every single engine except for your scramjet, because your scramjet works at supersonic speeds. So to do that, there's a couple ways that designers have got around this. So you have your intake here, it's like this, and so your air is coming in here like this, like this, like this, and it's going across the front of your engine. Your intake could look different. It could look like this Y shape from the top. It could look like an S shape if it's coming from the belly. There's a whole lot of different options that your intake can take, or shapes that your intake can take. So your intake will look like this because it has some thickness, right? Like that. And so what happens, or maybe it goes above, whatever. What happens is as your intake, as the air is flowing through, you need to make sure there's an even pressure distribution. And so when you're going really, really fast, what happens is you start to form shock waves, pressure waves, where you'll have a high pressure wave here, and a high pressure wave here, and a high pressure wave here, and that's bad for your engine. It essentially is like a sine wave, where you have like high pressure here, high pressure here, high pressure, low pressure, like stuff like that. That's not one-to-one, just a good example. But you have high pressure waves, and if that lands poorly within your engine, it'll mess up everything, like I said, blow your engine apart, which no one likes. So what these intake designers did, I'm gonna come over here where I have more space. They have your intake, but then they added little gates here that can move, like this. And so as your air is coming in at different speeds, these will rotate up and down at a different angle. I'm just gonna put delta as my angle because that's what I like to draw. It looks like a fancy little D. We'll do that. So these gates will open and close based on how fast you're going, which it gathers from sensors on the aircraft. And so what that does is it allows the air to come in and go up here and go through this bypass chamber, either to the afterburner or out the back of the engine or to the nozzle, whatever it may be. And that helps regulate your pressure within your intake to make sure your pressure here is even so you don't blow your engine apart. However, as some of you may know, more moving parts equals more parts of failure, more points of failure. So you want to decrease the amount of moving parts because then you need to service it and whatever. So to do that, someone that's way smarter than me, or maybe a couple people, company, whatever, had this design where there's a hump. And this hump can either be like, if this is the nose of your aircraft and this is your intake, the hump can be right here, or it can be on the top, like up here, whatever it may be, inside the intake. But what that does is they were able to use CFD, they were able to use math, whatever, to design this hump, and this hump does the same job as this without any moving parts. So as your air is coming in here, the geometry of this hump will make sure that you don't create shock waves in your intake, and those shock waves won't destroy your engine. So, yes, I think that is mostly everything that I want to cover. Let me just do one quick once over. So let me work on this. So, oh, that's one thing I wanted to cover. Okay. So you have your intake, you have your engine, and your engine has a cold side and a hot side based on where it is in relation to the combustion chamber. So everything past combustion chamber is hot side, everything before it is the cold side. So like your turbine blades that extract energy from your fluid to spin this, to spin your axle, are gonna need to contend with temperature, whereas these ones, generally speaking, won't. So if your engine, you have your afterburner, and then you have your nozzle. So air goes in your intake and you do a bunch of really fun stuff to make sure that it's very nice for your engine. Your engine compresses the air, combusts it in the combustion chamber, and then it spins this to make sure that the front can keep compressing. And then you have it go into your afterburner. Your afterburner adds energy and then blows it all out the back really quickly using your nozzle to optimize everything. All of this works to push a whole lot of stuff out the back, which then pushes your aircraft forward. So, I completely forgot what I was gonna say. Oh, yes, so your internal combustion engine for your car, for your early aircraft, whatever, you control those through fuel flow into them and spark plugs and all that fun stuff. However, that doesn't work for a jet engine. For a jet engine, you have all this spinning mass, and so to control how fast your engine goes, how much thrust, so when you push on that throttle, you control the fuel flow to these combustion chambers. So, more fuel equals more, that's a bad M, more combustion. So more fuel, more combustion, and we can control the more fuel. We can't control the intake because it's happening constantly. Whereas like on a diesel or your internal combustion engine, you can regulate how much air is going in at a time. Our engine is hungry at all times, doing everything at once. So we control the fuel, but because we control the fuel, we need to characterize through a set of math equations, through testing, whatever, to see, okay, 10% throttle does not always equal 10% thrust. 10% thrust. And so we need to figure out how we can get here. And so what happens is you can do a whole lot of testing, a whole lot of fancy math, where you create this math equation that will say, okay, I input a throttle signal of 0 to 100%, and the engine gives me a thrust output of 0 to 100%. And so you can do a whole lot of fancy math to figure out this block here that will tell you, okay, I give you a 10% throttle position, maybe that gives me a 23.5% thrust position. That is really hard, but it'll allow you to simulate the engine without having to go through all of like, okay, set it up, get the fuel, whatever. You can just do it on like a laptop or a computer or a supercomputer, whatever. But with your internal combustion engine, especially with the high performance stuff, you have your gas pedal that sits here, and you push your gas pedal down and your car revs almost immediately will start jumping up really, really high. That's because there's not a lot of mass in those tiny little engines. However, with how big these engines are, how big they can get, and you have all these spinning bits and all that, there's a response delay. So if I say, okay, I need to go from standing still to takeoff speed, so here's my throttle. So this is time. This is throttle position from 0 to 100%. And I say, okay, I want my throttle. I go from 0, nice even line, up to 100% throttle, like this. And then I just stay at 100% throttle. Well, your engine needs time to spin up all that, which is why, like, if you're on a commercial aircraft and you're sitting on the runway, you can hear the pilots as they increase, it'll go, woo, it'll get louder as everything spins faster. Poor noises, but hopefully it illustrates the point. But like, you need time to spin up because all this has momentum and inertia, and it's like really hard to get it spinning really fast because there's a lot of weight there. So as your throttle goes up, hopefully you can see this. You have your time and your thrust. There will be a delay. So if you start at 0 time, and you increase your thrust in a line linearly up to 100%, your thrust might look like this, where these two time points are different. So let's say this happens at 10 seconds, which is unrealistic, but whatever. And this happens at 20 seconds. So you now have a 10-second delay between when you tell it to do 100% thrust and when it actually does 100% thrust. And this little distance here is very, very useful, especially when you're like dogfighting or for like fighter aircraft, because you need, like, if you're in a position where you need to get a lot of thrust to either get away or rotate your aircraft, however it may be, this distance is going to dictate how quickly you can manipulate that aircraft. So you want to decrease this distance, the difference between your 100% throttle and your 100% thrust, your throttle position and your thrust position. And there's a couple of ways you can do that I won't cover today, mostly because I'm not super knowledgeable about them. Yeah, there was another thing that I was going to cover. I apologize. I'm not super organized, but yeah. So let me find. Okay. So we have our. We're going to go back to sort of the early part of what I was talking about, where each engine, each type of engine, so your turboprop, your turbojet, your turbofan, and then your ram and your scramjet, they all operate at different Mach numbers. And so if you have an aircraft that you want to go really, really fast, your options are afterburner to augment your thrust, to get you more thrust, or rockets. Generally speaking, we don't put rockets on aircraft to fly them. We don't put rockets on aircraft to fly them. So what you can do, or what some of these companies are now getting into, like Hermeus is just one company that I've been very, very interested in, is they're doing a thing called combined cycle engines. And so what that means is up here, you have your Mach number line. So your Mach number gets bigger, starts from 0, like that. And so your turbojet, your turbofan, this one, like your commercial aircraft use, will go from Mach 0 with an afterburner of like your military stuff up to Mach 3 with an afterburner. But let's say I want to go up to Mach 6 or Mach 5. Damn, that's bad. How do I get there? You can't with this engine. So what Hermeus is doing, and what some of these other companies are starting to get into, is combined cycle engines. So what they're doing is you have an outer casing that sits like this, and then you have an inner casing that sits like this. And so instead of using one of these, which is a high bypass, where you have a big area that goes around your internal part of your engine, they're using low bypass, so this area is pretty small on the inside here. So you have your nozzle. This is poorly drawn, man. Okay, your nozzle here, you have your blade 1, your blade 2, that go all the way around like this. So you have your turbofan, your turbojet on the inside. So this is in here. But what they're doing is your turbojet can only get you up to Mach 0.3. But your ramjet can get you from Mach 0.3 to Mach 0.6. So turbofan. So your turbofan gets you from takeoff to Mach 3. Your ramjet gets you from Mach 3 to Mach 6. So if you put these together, you can then take off from sea level and then get to Mach 6. So they put the turbofan turbojet inside the middle of an engine. And so your air's coming in through here, and you're doing all your spinny stuff and your combustion and your afterburner, all that fun stuff. But as you get up to Mach 0.3, what they're doing is they have their intake here. They have their nozzle, like I drew earlier. That's bad. Let me redraw that. So your nozzle here, something like that. What they're doing is then they have doors that will close. So these doors will normally sit like this, but they can rotate upwards like this. So this one's drawn not well enough. Like this, but these will rotate in the middle. So your air's coming through here, it's going around your intake nozzle, and it's flowing through your turbojet when these are open. But when you get up to Mach 0.3, where your turbofan no longer works because the tip of your blade is going supersonic and will break, you close that part of the engine off, so now you just have a straight tube, and then you have a ramjet, and your ramjet can go from the point that your turbofan ends at Mach 3, and goes all the way up to Mach 6. Sorry, not 0.6, 6. And so now you have an aircraft that, instead of needing to be dropped via a big cargo plane at 0.3 to get to 3. I don't know why I keep saying 0.3. That will get from Mach 3 to Mach 6. You now have an aircraft that can take off from a military base, take off from a commercial airport, and go all the way up to 6. So that gives you a massive play space. They're still doing a lot of work with this. Definitely a company to keep an eye on. I know I am. So those are combined cycle engines. The only problem is supersonic at Mach 1, as I'm sure hopefully you guys know. Once you hit Mach 1, you get a shockwave, right? So let me erase this, and we'll get into that briefly, hopefully. Okay, so you, as an aircraft pilot, your airplane, for now, is going to look like a missile. But as you go faster, as you start getting closer and closer to Mach 1, here's Mach 0, Mach 1. As you get closer and closer, the air starts to build up and goes from non-compressible to compressible. And that happens at Mach 0.3 when you enter the transonic regime. And so your air, instead of not being able to be compressed, like you can't push that any closer, you can now get that air down to this little volume with a whole bunch more, like that. But you do it just by flying. And so what happens is you're like if you're in water and you drag your hand through and you can see those waves that kind of show up on your hand, the same thing happens in air. And so you kind of have waves that are here. But the air can only get out of the way so quickly. And so as you get faster and faster, these waves, the distance, delta, again, that's a poor delta, whatever. The distance starts to slowly creep downwards because the air cannot physically get out of the way fast enough. And so when you hit Mach 1, the reason there's a sonic boom is because all of those pressure waves, so all of this air, all those waves now line up onto one. And so you get this nice big shock wave. And that sonic boom is caused by all these waves stacking up because this is a bunch of pressure waves that are all on top of each other. So you as a person are standing here and there's nice pressure around you at one time. But as this aircraft flies by you, there's now going to be a massive wave that looks like this, or maybe it looks like an angle, whatever it is, that is high pressure. And so that high pressure wave, as it comes over your body, your ears are going to say, that's really loud. Also, windows don't like it because windows are fragile. And so there was an aircraft called the Concorde that was a commercial supersonic jet. Due to some issues, no longer in service. You can look it up, there was a crash, a whole lot of stuff happened, but since then, commercial supersonic travel has not existed. However, NASA is trying to fix that. And so when you fly, let's say this is your aircraft and this is the ground. So you have all your houses down here, whatever, with all your windows. That's a poorly drawn window, whatever. If you fly supersonic over land, you're going to shatter these windows, you're going to injure people. At worst, you could kill them if you're going fast enough. And so what NASA is doing is they're trying to augment the design of their aircraft, so change the shape of the fuselage, change the shape of the wings, whatever it may be, so that way when you're flying supersonic, your pressure wave is directed upward, away from the ground. So now you can go supersonic, but your pressure wave is shot up towards the sky where no one cares, because it's nothing up there. And so you can fly supersonic over land, you can get places faster without injuring people or damaging property. And so this is kind of where things are at now. You have your combined cycle engines that Hermes is doing to push people faster. You have NASA doing research on pushing shock waves upwards so you can fly over land, and hopefully all that will come together so you can get on a plane in Los Angeles, use your combined cycle engine aircraft to be in New York in like an hour. But hopefully that'll be sooner than later. But yeah, I think that's kind of everything I had. Hopefully this kind of brought you up to speed on jet engines, jet stuff, intake stuff, afterburner stuff. And yeah, thank you very much.